This tutorial realizes a Vosim generator based on a DSP process written in the genexpr scripting language, making use of the gen object. In order to start writing code, a few basic characteristics of this scripting language need to be introduced. This introduction starts with regular objects before actual code is written. First of all, the history object is of great importance. It creates a one sample delay with the option of feedback. This means that the signal output can feed back into its own inlet, where it will be made available one sample later. A one sample delay is a fundamental building block for realizing advanced DSP processes. Continuously adding the value 1 once per sample can be defined as a feedback process. The resulting signal is sent out from gen through an out object. In Max, this signal is visualized with a signal number object. Instead of allowing the signal to increase indefinitely, with the wrap object the value wraps around to 0 when it reaches sample rate. The gen environment understands what this global value represents. Now, once per second, the resulting value indeed wraps around to 0. Another way of thinking about this wrapping is to define 1 as the upper limit and accumulate fractions which are 1 over the sample rate. The expr object can hold such expressions. This basically creates a phasor with a frequency of 1 ramp per second, or 1 Hz. The phasor represents an important concept in DSP coding, as phase-driven processes suggest transition from beginning to end in terms of a phase transition from 0 to 1. Very often, processes can be defined as repeatedly creating such a transition. The frequency of the phasor we have built can become variable by creating a param object, a parameter, which is referred to with a name, freq in this case, and is given a default value. After adjusting the expression, we again see a phasor with a frequency of 1 Hz. This parameter is exposed as an attribute through an attrui object and can now be changed. It should be clear that the patch we created is translated into a script. This happens on the fly. The script becomes visible by opening the Code tab through the toolbar. When an object is selected, the corresponding code highlights. Instead of relying on automatically generated scripts, it is possible to write our own in a codebox object. The result of the expression in the codebox is sent out a second outlet. As a first test, let's rewrite the code required to create a phasor. The first step is declaring a history which is referred to with a name and given an initial value. Following the logic of the generated script, the next step is to output the value of the history. Finally, the history value is updated by incrementing it and wrapping between 0 and 1. When comparing the signals from both outlets, we see identical behavior. There are a number of advantages of writing scripts rather than relying on object boxes, one of which is that the code in a concise manner can express what we try to achieve. The parameter can be defined in the code box as well. And just to check it is working, another approach to creating a ramp is introducing an increment value stored in a history. Incrementing the value for the ramp then looks like this. Wrapping the ramp can be done when it exceeds the given range, using an if statement. This is also the moment to calculate a new value for increment, in the case the frequency has been updated. This version behaves equally like a phasor. There is a difference, however, which becomes clear when the frequency is set to a very low value. When the frequency is again updated to be higher, we see that the codebox version will wait until the phase is completed before evaluating the new value for frequency. In certain situations, this can be an advantage. We should avoid, however, the frequency to be set to 0 because the codebox version will never update again. This situation could be escaped with a reset. Now that we know how to construct a phasor in genexpression code, we have understood enough of the fundamentals for the next step, creating a Vosim generator. Before going there, let's confirm the logic of Vosim, based on a paper written by the designers of it, Kaegi and Tempelaars. This paper lists all of the possible parameters that can be described for a full version of the generator and explains how the Vosim signal is constructed based on a squared sine. Here it also shows what a Vosim signal looks like given specific values for n, b, and t. Focusing on these three parameters, let's spend a moment to look at the math required to create such a signal. For the visualization, the application grapher is used. Following the logic of a phase-driven system, the first step is to create a phase that reaches a certain maximum for n, for instance 8. Clipping this phase between 0 and 8 is achieved by combining a min function, which produces the minimum of two values, and a max function, producing the maximum. This is what this phase looks like when graphed. Since 8, the value for n, is a parameter, let's define it as such. The next step is to take this phase as an input to a cosine in order to create 8 cycles of a cosine. When this is graphed, it is clear that something is wrong. The difference between a cosine in grapher and a cycle in max is that the first one requires a transition over 2 times pi to create a full cycle. Adding that as a multiplication factor fixes this. The function is turned into an equivalent of a squared sine by subtracting it from 1 and by halving the amplitude. The amplitude function that needs to be applied to this is constructed by raising the value for b to the power of x. The parameter b is defined as a variable. This amplitude can simply become a multiplication factor to the squared sine, but that's not entirely correct. The amplitude should be sampled at the beginning of a cycle. This can be achieved by flooring x. This result now can be tested with different settings for the parameters n and b. Now that we have covered the basics of the genexpression scripting language and understood the math behind constructing a Vosim signal, we can turn to Max and build a Vosim generator in a gen object. As a reference, I'll paste an image here with a graph of a Vosim signal and its 3 key parameters. A scope is used to verify the signal. Of course, a codebox object is required. However, instead of writing code here, I will switch to Sublime Text. This is an example of an editor which makes writing genexpression code much easier. For instance, after saving with the genexpr extension, it will highlight the code according to a theme friendly provided by Emmanuel Jourdan. More information can be found here. The first step is creating a history. We immediately see the advantages of the highlighting and autocompletion. This history represents the ramp from 0 to the amount of pulses. The increment for this ramp is defined as a history as well. When parameters are defined using autocompletion, we see that it is possible to define options for min and max. The first parameter defines t. Instead of thinking in terms of milliseconds, I prefer to work with the frequency value instead. Other parameters define n and b. Following what we have seen in the introduction, as a final expression in the code, the ramp history needs to be incremented in order to create the ramp. That implies that somewhere a check needs to be performed for when the ramp goes beyond the limit, not 1, but the amount of pulses. That is again the moment to reset the ramp and calculate a new increment. The variable c will hold the value for the cosine signal that is read from a wavetable using cycle. It is fine to define variables in this way without any other declaration statement. Since typically the cycle function regards its first argument as a frequency value, the index parameter needs to be set to phase. The Vosim signal that we output can be defined in a similar fashion as we have seen in Grapher. Next, we need to apply a decaying amplitude signal. This amp again is exactly defined as how we have seen it in Grapher. Although this is not a complete Vosim signal, it is fine to try and see if this works inside Gen. Getting the code there requires the use of copy-paste. When the audio is enabled, a signal indeed shows. Zooming in confirms that it looks like what we would expect. Of course, it is also possible to listen to the signal. That sounds already quite like it. Another UI is again used to expose parameters. This one allows for changing the frequency. Now let's test the other two parameters as well. In order to turn this into a true Vosim, a delay needs to be added defined by m. I will take another approach, however, and define the length of a full Vosim period with another frequency value. This requires the construction of a second ramp as well as the corresponding increment. At the end of the code, we can add the incrementing. In addition, we can expect that before the ramp for the Vosim period is completed, the ramp for t reaches n, the value representing the amount of pulses. This ramp therefore needs to be limited, which is done with a min function. The Vosim period ramp reaching 1 will now trigger resets for both ramps. A parameter for the frequency of the Vosim period needs to be defined, so that the increment can be calculated. Now let's see what this does. First, let's create access to the newly defined parameter. This all sounds promising, but I see a problem. It can occur that the Vosim period hasn't enough space to hold the prescribed amount of pulses. The construction of pulses is then interrupted somewhere in the middle. This needs to be repaired. The approach I will take is limit the parameter n by defining a new history. For the default frequencies of 1000 for the pulse and 100 for the Vosim period, it is clear that the maximum that n should reach is 10. The value for max n indeed can be defined by calculating the floored division and limiting the result to n. Let's see what this does. Indeed, it appears to solve the issue we noticed earlier. There is now a space between two trains of pulses. This sounds fine to me. However, I'm not so happy with the frequency values. Instead, I would prefer defining pitch values. This can be achieved with some small adjustments in the code. The parameters for t and v will be renamed. The default values will be set to 90 and 30. The calculation for increment requires an m2f function. The division used to calculate the limit for n now doesn't make a lot of sense anymore. But that can be adjusted by simply taking the increment values as input for the division. With these final adjustments, the pitch of both aspects of the Vosim can be controlled easier. And through the use of a picked slider, we can interact with both of them simultaneously. This tutorial ends here, but I'm sure you see a lot of aspects up for further development.